Welcome everyone to today's virtual meetup, webinar, whatever you prefer to call it. We have Felix as our guest today and as our speaker. Felix is a colleague of mine who works on the Java agent for APM. And he will talk about some really new feature to get some more visibility within the Elastic APM Java agent. That's for now all I have to say. My name is Alex. I'm part of the community team. If you have any questions, please put them in the chat. We will collect them so we can do a Q&A at the end. They don't need to be Java APM specific. If you have an APM question, if you have a generic Elastic Stack question, please put them in there as well, and we try to cover them at the end. And with that said, I will just hand it over to Felix, and Felix will get this going.
Thanks, Alex. And thanks for tuning in to my webinar about getting more method level visibility with the Elastic APM Java agent. So the subtitle is also from distributed tracing to distributed profiling. So we're going to talk about some profilers today, and I will tell you what distributed tracing actually is. As Alex said, I'm working on the Elastic APM Java agent, and yeah, my name is Felix, and let's go. First, I'm going to tell you about what distributed tracing actually is, then some ways how you can get more method level insight with the Java agent. Then I'll give a short demo how to instrument a Spring Boot application. And then we'll dive into some more theory on how profilers work and how the profiler that is built into the Elastic APM agent, how it actually works. So first of all, tracing. So what is an APM agent and what does it do? What kind of information does it collect? So when you're looking at your Java applications, those are typically running on servers, right? So you can have multiple of your Java applications running on a server, and you can use our agents to collect some information from those Java applications. So those agents are sitting within your Java application, and they are instrumenting the application to get some details of what's going on in those applications. So we are collecting details about mostly the incoming requests and the outgoing requests. So you know how long it, for example, takes to serve a search request on your e-commerce website, and you can see how that behaves over time. And you can also dive a little bit deeper and see what kind of requests you're making to other applications. Maybe you have some sort of microservice-based application, or even if you don't, you probably use a database or something where you do some requests. And often these external requests are a source of latency, which basically make your application slow. And our agents can help you to identify those. We're also collecting some metrics, and all of that information is then sent to the APM server, which processes that information and sends it over to different Elasticsearch indices. And then there's also a APM application within Kibana, which you can use to see to visualize what the application does. And you can not only use the built-in visualizations in our dedicated Kibana APM app, you can just go ahead and use create your own dashboards, your own visualizations, because everything we store with APM is just another index in Elasticsearch. All right, what is distributed tracing? So I told you that our agents instrument external requests. So we also instrument outgoing HTTP requests, for example. And we do that not only to show you why a request was slow, or how long did it take to call that downstream service or that endpoint. And what we also do is we inject tracing headers into those requests. So with that, we basically can reconstruct how a request went through your different services. So if you have multiple services that are involved in answering a user request, you will be able to see which of the services were involved and how long which service took. So basically, you can then blame a service for being slow. So we also provide some more high-level information. For example, the span time spent by span type. In this example here, you can see that a lot of time was spent doing outgoing HTTP requests, and only 27% of the time was spent within the application itself. We also have visualizations for the transaction duration, so you can see how your requests are behaving over time and how many requests your application is serving. And that is also broken down by HTTP status codes, so you can see all of your 200s and how many 500 requests you have. All right, so once you've identified your service, sometimes this is where APM tools sort of stop giving you valuable information to troubleshoot that latency. So I told you already that we're instrumenting outgoing requests, but what if your application is not doing any outgoing requests or any database requests, but is still slow? What do you do then? So you basically end up then with something that looks a little bit like this. You have a big request that takes 5.5 seconds here, and you only see one span. So this is called a span. It's basically an operation or how long one operation took, and it has some metadata associated with it, like the name of the operation. And yeah, here we can see we only have one such operation, and it only took around half a second. So we don't know what happened for 5 seconds here. So what we now want is to have some more method level insight, which methods were called and which caused the service to be slow. So of course, not all requests are slow, can be slow because of external requests. It can also just be like inefficient algorithms or something of that sort. So for that, you need that method level insight. And the Java agent gives you multiple options to do that. So one option is to use our API, which means you have to code something in your application. That is the most flexible of the approaches. You can customize it really well, but it requires code changes. What's the problem with that is that you basically have some sort of chicken and egg problem, because you might not know which are the methods that slow you down, but you also have to know which methods you want to instrument. So yeah, you have your classical chicken and egg problem right there. And it's also a bit verbose, and you can do some things wrong when using the API and corrupt the state of the current and the following transactions. That doesn't mean that your application is suddenly creating errors. It just means the tracing doesn't really work correctly. So how you do that is you add a dependency to your application, to the APM Agent API module. And this is how it looks like in code. So you can create the current span and create a child span of that. And then you have to activate it, which means it puts it on the current thread and also helps with log correlation. You can set a lot of details like the span name and labels, for example. You can capture any exceptions that could occur in your business logic. And finally, you have to end the span. What's really important as well is that the scope is closed, because otherwise you can leak the scope into other threads. So lots of things here you have to remember. But there are also ways to make that a bit simpler and less verbose. So you can use an annotation-based API, and so there you don't have the danger of corrupting state. It's less verbose. You don't have to code everything explicitly, and you can even combine that with the programmatic API to still be able to add custom labels. So that basically uses bytecode instrumentation. You annotate your methods with a special annotation here at traced, and that basically does almost the exactly same thing as this one, and the span will be named just after the method here. And then you're still able to just get a hold of the span which is created by this by just calling current span. And then you can customize the span. You can set custom labels, maybe based on the method parameters even, or you can set a custom name, for example, or a different timestamp or whatever. So then there's another approach, and that is with the configuration option trace methods. And the big advantage here is that it doesn't require any code changes. So instead, it provides some sort of syntax where you can specify all of the methods you want to instrument. So for example, by package name, and here you can also use wildcards. So this org.example.star means it instruments all of the methods and all of the classes in the org.example package or in any of the sub packages. You can instrument methods by their class name, and you can also mix that in with wildcards again. So you can instrument all of the methods that end in service, or you can, of course, also specify an explicit method. And there are many more options you can use to select your methods. You can read them up in the documentation here. All right. The big downside here is that it's really easy to overuse, and so how that works is every method that gets matched with such a matcher will also be instrumented with bytecode instrumentation, similar to the annotation example I showed you earlier. And the problem here is that we have to be aware of the performance impact. So don't get me wrong, just instrumenting one method maybe adds a couple of microseconds of overhead, but you have to be aware of which methods you want to instrument. For example, if you have a method that only takes around like a couple of nanoseconds on its own, and it's executed lots of times within a single request, you can get a massive overhead by instrumenting that method. And especially when you match a whole package, there's a good chance that you that you hit such a method. It can also just result in massive amounts of spans being created. And then there's the new kit on the block, that is the sampling profiler, which is now new in the Java agent. And that leverages a low overhead profiler called async profiler. So that is a very popular open source profiler that is, for example, also used in IntelliJ. With that, it is safe to run profiling in production. And you don't even need to specify any methods upfront. It should instrument. It just basically looks at the current stack trace and bubbles up all of your slower executing methods, no matter if it's in your code base or some library you're calling or whatever. So currently that feature is experimental, and we're currently looking at some improvements. So currently there are some issues with some parent-child relationships, which basically means that sometimes the order of these spans can be a little bit off, but you can just give it a try and give us feedback. That would really help us out. All right, so what are some of the use cases where you would use such a profiler? So for example, during development, to just find out why the request you just made was slow. also in load testing or even production, to find out why some requests are slower than others. You can then just compare fast executing requests with slower ones and see why the slower ones are slower, or which methods slow it down. It can also be useful for customer support. So if your customers are calling in and complaining, yeah, the request I made an hour ago was really slow, and then you can just go into your APM dashboard and see which methods caused that request to be slow. So here, a little summary table. Again, we have our sampling-based profiler, which is really low in overhead, no code changes required. And one downside, though, is that we don't have window support, and we also don't have exact durations here. So these are more like estimates, in contrast to all of the other methods, which really measure the duration of your methods. That's just the trade-off here. So it's not as exact, but it's usually good enough, and it's really low overhead. All right, then you have your API code. It's really flexible, but it's easy to misuse. We have the annotations, which makes it easier. A bit less flexible on its own, but combined with the API, it's also really powerful. But with those, again, you have to know which methods you want to instrument. Then we have the configuration-based approach. And that's really great if you want to do something with no code changes, or you want to look into your third-party libraries. And you can match many different methods with wildcards, but this is also leads us to this downsides, because it's easy to overuse and can hurt the performance. All right, with that, let's jump into the demo. So let me pull up my console here. So here I have a Spring Boot application. The Spring Pet Clinic, maybe some of you are aware of that demo project. And what I'm doing here is basically just attaching the Java agent, and I give it the location where it should send its data to. So let's just start that. We can see that it already detects the name of the application. So it sees the name Spring Pet Clinic, and that is based on the name of the jar here. Okay, the application seems to be running. Let's go to the browser and just click around a little bit. Okay, so far so good. Let's go to the home page, and wait a minute, that really takes a long time to load. I wonder why that is. So let's go to the APM application. Refresh it here, so we can see we have our Spring Boot application, which got discovered. We already have data in. Let's not worry too much about these charts. Here we can see all of the different endpoints which got detected. And so we clicked on the find owners here, which basically corresponds to this transaction here, the init find form, and the homepage corresponds to the welcome controller welcome. And this is the one we are interested in, right? So this one took a lot of time, so let's dive into that one. So that is basically the scenario I showed you earlier. We now see a span that takes 5 seconds, and then there's a massive gap, and then a small span. So we can get a little bit more detail here. When we click on that, we see some metadata like the cookies, the HTTP headers. We see some information where the service is running on, and some process information, the URL and so forth, but nothing really helps us to dive into or to find out what happened here. So why not just use the sampling profiler I just told you about to find out what happened here. So that is the same command I'm going to execute in a second here. But I'm adding two more options to the Java agent. So first, I'm enabling this experimental profiling feature, and I'm also setting a sampling interval to 10 milliseconds. So that basically tells us how often we want to look at the stack, and how accurate the results should be, and how also sort of determines the level of detail we're going to get. But more on that later. All right, let's wait a second for the application to start up. And go back to the application and execute the homepage. All right. Let's reload the information here. And we've got another request. Let's go into the details here. Okay, now we have a lot more detail. We even see what's happening inside the view rendering. We can see which of the methods got executed during that request. And we see that like the fastest methods are around 10 milliseconds. And that corresponds to the sampling interval we set in the Java agent options. So basically, by setting that, you can determine the level of detail you want to see here. If you don't want to see all the really fast executing ones, you're only interested in maybe methods that only take longer than 50 milliseconds or 100 milliseconds, you can use that option. And here we can also see a bit of an inconsistency, and that is something we're already working on fixing, because that one should be ordered above this one. And we can now also find out why the request is so slow. So here we can see all of the methods, and they all seem to lead up to this method here, welcome control think. So let's maybe go into our IDE, see what the welcome controller does. And yeah, for demo purposes, I just did a thread sleep here, but we found that out with the profiler, which is pretty great. All right, so much for that. So let's go into the theory again, how profilers work, how does the profiler here work, and what's that magic anyways. So mainly we have two different types of profilers. We have instrumenting profilers and sampling profilers. So the instrumenting profiler is something like the trace methods option I showed you earlier. So where you can specify all of the methods you wanna trace, and that inserts tracing points into all of your methods. So all of these little blue dots here are points where we get the timestamp, and then we get the timestamp again at the end of the method. Then we know how long this method took. So while that is somewhat maybe more exact, it's a real measurement how long that method took. But there's also really there can be a lot of overhead associated with that kind of approach. Especially the more methods you want to instrument, the more overhead you're going to get. But even if you're only instrumenting one method, if you pick the wrong one, your performance will be really terrible. So, and one of the reasons that is so we are inserting code here, and that can get in the way of some of the optimizations the Java virtual machine is doing. So one of the things the just-in-time compiler is doing, that basically looks at your methods and tries to optimize the hot methods. And one of the most effective options is to do method inlining. So for example, let's assume method E is really a method that doesn't contain a lot of code, and E is called from D. So why not just get rid of the overhead of the method call, just inline everything within E to D. That's a great optimization, but that only works if the code size of the method is really small. And when you add some tracing code to your methods, the code size can get over a certain threshold, and then you can't inline it anymore. That's just one of the ways how this can make things slow. So then we have a sampling profiler, also sometimes called statistical profiler. And that basically works by looking at the stack trace at a fixed sampling rate or sampling interval. And that is basically the configuration option I showed you earlier where I set the interval to 10 milliseconds for the Spring Boot application. And so here the overhead is only proportional to the sampling interval. So the more accurate information we want to get, the smaller the interval, but also the higher the overhead. And sometimes you don't really want all that fine-grained detail. You just want to see what are your slow methods. Then you can also get away with a much larger sampling interval and with much less overhead. But there are also some things on the profiler with sampling profilers you have to be aware of. So, for example, here we don't really see the method E. That can be, as I said, a good or a bad thing. It can be a bad thing because you're not aware that this method is even there or even called. But it can also just remove that clutter, basically. All right, then there's also something called periodicity bias. Because we are only looking at the stack trace at regular intervals, we might misinfer some methods. So here, for example, we don't even see the method C. We only see the method B. But we think the method B is really a long executing method when it just got executed a lot of times. Then we have another bias, which is called the save point bias. So that affects basically all the typical ways to get a stack trace in Java. We have, for example, the thread mxbean get thread info or the dump all threads method, which tells you about the states all of your threads are in, gives you all the stack traces of those threads. And there's also the jvmti method get stack trace. So that's basically a native method, but even that is affected by the save point bias. So not only you can get inaccurate results because of that, but it can also significantly slow down your application. That is because stack traces can only be taken at a global save point with these methods. And that basically means we have stopped the world pauses here. So all threads have to wait for all other threads to reach a save point. And it can frequently take several milliseconds to reach a save point. So that might sound all a bit theoretical, and let's get into a bit more detail here and see an example later. So what is a save point even? So that is the point in time where the JVM can do some bookkeeping tasks like garbage collections that requires basically all threads to be at a global save point. And also to get the stack trace, as I told you, we have to be at this global save point. And basically how it works is all threads are constantly polling a flag that the JVM sets. So if the flag is false, it means there's no save points to enter, but if the flag is true, all threads try to reach that save point. And this thread, or the polling of this flag is done when you enter a method or when you exit a method, and at the edge of uncounted for loops. But there are also a lot of areas where there's no save point or no save point pool. So for example, in counted loops, in inline methods, or in JVM intrinsics like system array copy and direct byte buffer get. So the last one can be really bad. So when you read from when you want to read from a memory met file, that can get stuck on a page fault, meaning it wants to load more things from the disk into memory. And if the disk, maybe you have a spinning disk, if that is occupied by other processes, it can take a lot of time to get the result. And basically all other threads have to wait for this method to finally end, so that we can reach the global save point. So maybe let's look at an example that will, I guess, make things a little bit simpler. So in this scenario, we have 3 different threads, T1, T2, T3. And T1 wants to get the stack trace for all of the other threads. So it calls the thread mxbean get thread info, or dump all threads method for that matter. And that basically flips the switch or the flag in the JVM, which means a save point has been requested at this point. So now we have to wait for all of the threads to reach a save point. Then we have this blue bubbles here again, and this time it means there's a save point pool in these areas. So when we look at T2, at the time we requested the save point, we are within a method B, so we have to wait until the method has completed. So at this point in time, we're then looking at a new, we're polling the save point again. And then this thread really has to wait for all of the other threads to also reach a save point. So let's look at T3. At the time the save point was requested, we are within a JVM intrinsic method in system array copy. So this method is, for example, called when an array is resized. By default, it's initialized with a size of 16. But once you add the 17th element, the array has to be copied into a larger array. And if that array to begin with is really large, then the copy can also take a lot of time. So this method here in this example takes some time. So we have to wait for this method to end, and then we can finally reach the save point again. But during this time, this thread and potentially a lot of other threads can't do anything. So there's a stop the world pause. So no user request can be served within that time frame. And so at this point in time, we finally are entering the global save point, and we can get the stack trace of all of the different threads. And the time between save point requested and global save point is called time to save point. And this can also be monitored with JVM flags. So you can get a log with how long it takes for all of your threads to reach a save point and how frequently that operation happens. Then there can also be, as I told you, inline methods. So the just-in-time compiler has decided it's more efficient to inline the method E into method D, and then we also lose the save point pause in that process. All right, yeah, so much for all of the different biases for the profilers. Now introducing async profiler. Now that is the profiler we are using in the Elastic APM Java Agent, and that is a really nice profiler. So it's a native sampling profiler, and it's automatically shipped and configured via our Java agent. And again, this async profiler is also used in IntelliJ, for example. And that uses a different way of getting the stack trace that doesn't have the save point problem. So it uses the async get call trace API that is an unofficial API of the JVM. And it has many edge cases. It's not easy to work with. And so in some situations, it just can't get the stack trace. So that is also, one example for that is also JVM intrinsics. So when you're within system array copy, normally there's async get call trace API can't traverse the stack trace when you're within that method. However, async profiler has implemented some sophisticated fallback strategies, and it's still able to traverse that stack trace even in those situations. But most other profilers you might know, like Honest Profiler or Java Flight Recorder, they which are also based on the async get call trace API, they can't get the stack trace, for example, when within JVM intrinsics. So one downside of async profiler is it has no window support. It's again, it's a native profiler, and this async get call trace API is also a native API within the JVM. So you can't just call it from within Java code. And because we are really big fans of async profiler here at Elastic, we also want to integrate it more and more in our product. So we're currently looking at how we can integrate the CPU lock and allocation profiler capabilities of async profiler. So what we want to do is to have some flame graphs where you can, for example, see the CPU flame graphs of your applications. And so you can focus on larger timeframes with that. You can also see multiple services aggregated in one flame graph to see which methods burn your CPU. And that is also super useful to identify methods that are actually quite fast to execute, but when they are executed quite frequently, they can still cause a lot of pain and a lot of burned CPU cycles. So CPU flame graphs are really useful, but they are not that useful to troubleshoot latency because they only show you what's happening on CPU. When you're doing a lot of external requests, chances are that your threads are not on CPU, but they're actually just waiting for the response. So you wouldn't see that information in CPU flame graphs. But for that, we have the profiler-inferred spans, basically the method level detail feature I showed you earlier, and which basically then allow you to answer the question why this request was slow. And focus here is on the elapsed time, and also called wall clock time. So final words, all that I showed you today is free and open, so you can just go ahead and download the Java agent and the Elastic Stack. You can either host it yourself on your local machine or just in a data center. You can also let us host it on the Elastic Cloud. And if you want more information around all things Elastic and APM, we have a lot more webinars on our website. We have some examples you can just where you can just click through dashboards. You can chat with us in the Discuss forum, and in the documentation you can also find a lot more details of what's supported with the Java agent, for example. And we also have training for APM and other things. So with that, let's open it for questions. So for production, we should probably go with the async profiler. Is that already JA or beta? So async profiler itself is a widely used profiler. It's used by a lot of companies, and it's basically GA. But our integration with async profiler is currently experimental.
Just to be sure, which version will this gonna be released in, so everyone is aware of that.
The first version with the integration of async profiler in the Java agent is 1.14.0. Currently, we are at 1.15, and we don't know when this will be GA yet. So we are also waiting on just user feedback on that.
Yeah, it might be important to note that this is not tied to the regular Elastic Stack releases that you see every now and then, like 7.6, 7.7, 7.8, and so forth. But this is released separately.
Right. Yeah. So the agents have their own release schedule. So, all right, what is planned for the next releases of the Java agents? We have a lot of things going on in the Java agent. So currently we're working on Webflux, for example. We are also working on, so Webflux is a web framework from Spring, similar to Spring MVC, but for reactive processing. And then we are working on better integration with logging. So what we can already do is when you also centralize your logs with Elastic, you can jump from APM to logs, and you can also jump from the logs to APM. So you basically know which were the log lines executed within that request, or vice versa. When you find something weird in your logs, what is the context of that log? Which other logs have been executed in that request, or even which parameters did the user specify in the request, or which things did they type in the form in the HTML page. And yeah, we are working on better integrations with logging so that the agent can send up the application logs without any configuration. So these are some of the things we're working on. Integration with other tracing solutions. So we do have integration with Jaeger, for example. So you can just use if you've instrumented your application with Jaeger, you can point it to the APM server, which can also just understand the wire protocol of Jaeger. And we do also have integration with open tracing. So you can use the open tracing API to either manually instrument your application with Elastic APM, or to even combine it. So you can use, yeah, I showed you the example earlier, right, where you can use the API to manually create spans. You can do the same with the open tracing API. So the async profile doesn't have exact durations. Is there any number of how off these can be? Yeah, that is basically determined by the sampling interval. Let me quickly pull up the documentation of the Java agent.
Yeah, you can probably also just paste the URL into the chat so others can take a look after that.
Yeah, do that as well. Now the Zoom controls are on the way. All right. Profiler configuration options. Then you have your sampling interval. That will basically determine how off things will be. So by default, the default value is 50 milliseconds. So it would be 50. It can be 50 milliseconds off. You can set it higher or lower based on your requirements. So that's basically the trade-off between accuracy and performance or overhead.
Yeah, there was a question from Corey in the Q&A and also in the chat. Are there standard APM dashboards available or planned?
Standard APM dashboards. So we do have the curated experience with our APM app. So that is basically a tab in Kibana where you can click through all of the different dashboards. I demoed this earlier. There are also many other pages where you can see errors, for example, or JVM metrics. But you can also just use you can also just create your own dashboards as we say, it's just another index within Elastic. So all of the information is just, all of the traces, all of the metrics are just stored in a regular Elasticsearch index. And so you can use your custom dashboards as well. There's also a contributing repository on GitHub where users share their custom dashboards.
Yeah, that said, I think everything you showed today is part of the APM app within Kibana, right? Like the traces shown and so forth. So this is already available and you don't need to add anything or create any dashboard manually within Kibana.
Exactly. And that is all, again, free and open. Configuration-based question. When creating spans for many methods, is there a measurement of the overuse or a warning when the agent is started? No, currently there's not. So you would just basically find out that your application is slow, because we also don't really want to restrict you in what kind of methods you want to instrument. Having said that, there are some ideas where we manually, or where we can basically detect, like when a method was really fast, let's say it was faster than 1 millisecond, then we could go ahead and remove that instrumentation from that method. So these are some of the ideas to get rid of some of the overhead involved in trace methods. But yeah, when you create a lot of, or you want to basically measure your whole code base, and if you want to do that in production, it's better to use the sampling profiler approach.